beautiful work. And Nathan Youngblood, and he's going to talk about scalable architectures for controlling computed memory using non-volatile optical materials.
Thank you very much. It's a pleasure to be here, give a talk on more of the hardware-centric side of things rather than the software-centric side of things. So my lab and in collaboration with some of our international collaborators, we've been working on ways of scaling up the hardware that surrounds these compute problems rather than focusing on the actual algorithms. So it's good to kind of have both sides of the story. And hopefully calling it scalable architectures based on this morning's talk is not too controversial, but I appreciate Alex for giving a great introduction and motivation for the types of things that I will be talking about today. So to briefly motivate my talk, I don't need to go into too much detail about the demand for AI services, but something that I would highlight is that we're seeing a transition from training-intensive compute usage to inference-intensive compute usage. And this has become kind of well known after the release of OpenAI's o1, where you can significantly increase the performance just by giving a large language model the ability to think. And thinking is just inference and then looking at its inference and feeding it back in and completing the cycle. You can see that as you increase the test time compute, so this is on the inference side, the thinking side, the accuracy can increase dramatically. And in addition to this, OpenAI and all these other companies have been working on deploying these neural networks that they've trained. And so, in fact, while OpenAI is one of the leading institutions or companies that is working to train, frontier models, only 40% of their compute resources and money is spent on actually training these models. Now they're focusing more on deployment. And in deployment, we have models that think for longer and require more inference. In addition to that, we're also seeing that the digital accelerator landscape is going more toward integer 8 representation of these numbers. So you need floating point for training, for backpropagation and accurate representation of the gradients. But for inference, integer 18 and quantized models is actually much more beneficial in terms of throughput. And so the hardware is supporting both of these, and integer 8 actually produces much higher compute performance. And this actually gives us an opportunity for low precision analog accelerators on the inference side. So that's one side of things with billions of parameters that we need to compute. On the other side, there's also a growing need for computing in a low latency or ultra low latency side. We saw some for the icing machine where you're kind of bottlenecked by the speed at which you can do the FPGA matrix multiplications. So on smaller scale, these are some examples, including Natalia's nice work with Microsoft on solving optimization problems. So anything where you need to have ultra low latency, you're not as concerned about the actual energy, could be an optimal application for photonic computing. So photonic integration provides significantly smaller cross-section at the extremely high bandwidth of optical fibers. You have access to low energy linear transformations like Fourier transformations. And we also saw some nice results on less than 1 photon per multiply accumulate operation. So you can have very low levels of power. The landscape is continually growing, and these are just a smattering of some of the well-known works out there. So we have free space, we have coherent, we have incoherent options, we've got fiber-based dispersion options, and time-multiplexed deep neural networks. And these can be kind of broken up into two classes. We have weight stationary architectures and output stationary architectures, and I'll get into what that means. So for weight stationary photonic architectures, we take a problem. We maybe have the hidden layer of a deep neural network. We take these trainable weights, which can be mapped to a matrix vector multiplication. We translate that into some sort of physical hardware. And at each of these nodes, we have some sort of photonic memory or a need for photonic memory or reconfiguration of the matrix. So There's a lot of different ways to do this. My area of research is more focused on non-volatile photonic memory technologies, which I've kind of listed here. And specifically, we've worked a lot with phase change materials to encode information in the optical domain. Phase change materials, if you're not familiar with them, they're on the bottom of rewritable CDs and DVDs, and it's these chalcogenide glasses which can switch between their glassy amorphous state and their crystalline state, which has a huge change in the refractive index, some of the largest changes in refractive index known to optical materials. And they've also been used for electrical storage, so you can have a single device which stores information both in the electrical domain and the optical domain, and we've shown in the past that you can convert information between the two and read and write in both domains. So how do we use this for computation? So you can take this material, you sputter it onto a waveguide, and because you're changing the fraction of amorphous versus crystalline material, and there's a significant change in the refractive index and thus the loss for this particular phase change material, you can encode information optically by changing the transmission. So this is similar to resistive crossbar arrays or in the electrical analog domain where you're changing the conductance of these materials. So we change the transmission between 0 and 1. And when we combine that on a waveguide and combine two waveguides together, we can have an input power multiplied by a transmission, an input power multiplied by a transmission, sum those up, and we get vector-vector multiplication in a very trivial form. So how would we scale this up to something more useful? We can take, for example, convolutional edge kernels. We can map these to a 4x4 matrix and then map that to a crossbar array in the photonic domain. And what this crossbar array does, it does fan out along the rows and fan in along the columns. We sum these incoherently on photodetectors, and we're able to, as we sweep over 4 pixels at a time, get these output images that highlight different edges of the original input image. This is an example of matrix vector multiplication. But because we're in the optical domain, we have access to terahertz of bandwidth, so we can actually scale in frequency space, which is pretty cool. So now instead of just spatially determining the matrix size, we can input multiple input vectors at the same time, encoding them into different wavelength bands, and then we have kind of this alternate dimension that we can scale in for increasing the compute throughput. So for an example, if we send in 2 input vectors at the same time through the same matrix, we can increase our throughput by 2x. And we've shown that in the past that we can do this with optical frequency combs. So we have a single CW laser pumping a microring resonator, generating 4-wave mixing, all these different frequency bands, nicely spaced to 100 gigahertz, telecom standard spacing. And we can use standard fiber muxes and demuxes to do, 4x computing at the same time. So you can either have, 4 times the input images or go through the input images 4 times as fast. And so the frequency comb was provided by Tobias Kippenberg's group in these experiments. Okay, so that was kind of a quick overview of kind of the motivations of why we would want to do computing in the optical domain for matrix vector multiplication. But there are some challenges that Alex addressed in the first talk, which is what happens if your physical hardware does not actually meet the problem size that you're interested in. So let's say that we can only encode 4 or K by K matrix elements, physically on the hardware, but we have a much larger matrix that we want to do multiplication with. We'd have to reprogram that array multiple times. So we can either have spatial parallelism. Let's say that we have 100 million parameters. We need to encode that in a conservative, 20. Well, I guess this is pretty realistic. 25 by 25 micron unit cell. This would require an 8 by 8 centimeter chip. This is not realistic in terms of fabrication or practice. You can reprogram the array, and let's say that you have a 64 by 64 array, which is a little bit more reasonable. You'd have to rewrite it over 2,000 times, spend almost half a kilowatt of energy rewriting it, and have a ton of latency because you reprogram it. These materials heat up, and then it takes a little bit of time for them to stabilize. So there's been some analysis done by computer architecture people that say you can do computing very quickly. You don't have to have any static power, but if you have to rewrite the array, you actually spend the majority of your time and energy in terms of rewriting the array. This can be as bad as 1,000 times to 5,000 times in energy and time. So what we really need is something with photonic memory cells that those memory cells can be rewritten very quickly so that we can make use of the high speed throughput, but reconfigure the matrix quickly. And some requirements and additional requirements would be high programming endurance so that we can do this many times, fast programming speed, low programming energy, non-volatile ideally, so that they, if you don't need to change them, they can just stay there without any energy, multi-bit operation, compact footprint, and CMOS compatible voltages to make this all realistic. So how do we address some of these challenges? So one approach would be to take these phase change materials and do some sort of multifunctional memory cell. And what I mean by that is, let's say that you're training your neural network or updating the weights on your neural network. You can have kind of two regimes where you have a large change that you make use of the non-volatile phase change of these materials. And then you can also have these high-speed weight updates that are volatile, but have a small change. And so you can increase the precision and also have, small changes where you're not actually having to spend energy and time rewriting the phase change materials themselves. So some way that this might work is you have this ring resonator with a modulator, and these PN modulators you can etch down to the waveguide through the oxide and put these phase change materials on them. And so if you reverse bias these PN junctions, you're actually sweeping out carriers. This is a fast process that allows you to modulate these, Mach center interferometers or ring resonator modulators very quickly, but the range that you can modulate is quite limited in terms of the change in refractive index. But if you incorporate a phase change material on there and you forward bias these PN junctions, you can actually generate quite a bit of heat. So this is some simulations of the heat that is generated across these waveguides that are doped P and N type. And in here, if we reverse bias, we have volatile tuning just from standard PN junction modulation. But if we forward bias, we can have coarse tuning where it actually heats up the phase change material and changes it in a non-volatile way between its crystalline and amorphous states. So we can reconfigure, we have an example set of devices where we have four different rings. On one side, we have these small phase change material sections, and the other side in these rings, they're PN modulators. And we can address one side versus the other just for efficiency's sake. And so we can reconfigure the position of these resonances in a non-volatile way by forward biasing these devices with some relatively discrete, 3 or 4 bit of precision. So we can blue shift these resonances in a non-volatile way. But we could also volatilely change these devices as well. So this is an example of changing the phase change material, reverse biasing the PN junction, turning that reverse bias off, and then resetting it back to its original crystalline state. And so you can see that you can have multiple coarse levels from volatile or non-volatile tuning of the phase change material, but you can also, fill in those levels in a continuous manner by reverse biasing these devices. So one of the reasons that you might want to do this is, for example, in these phase change materials, SBSE, which have much lower loss and therefore don't kill your resonances in your Mach center or your ring resonators, they have relatively low endurance at this point. So this is an active area of research. But if you can reduce the amount of times you're switching these, you can extend the lifetime of your architecture. But can we do something even better than that that has better energy efficiency and better endurance? If you're interested in addressing endurance and phase change materials, there's a nice work from JJ's group. I think it's now been published online. Okay, so that brings us to our second approach, which is using non-reciprocal magneto-optics for phase change or for photonic memory, compute and memory. So these magneto-optic devices are used for optical circulators. There's been a nice work on high-speed cryogenic modulator by Paulo, our collaborator. And also non-volatile optical switches where you can encode information in these patterned Coffee-B magnets. And by switching the direction of these magnets, you can actually change the resonance position. So this prior work inspired us to collaborate with Paulo and Yuya, the authors of these two papers, to propose and demonstrate a non-reciprocal photonic in-memory computing platform. So in this case, the array is composed of these non-volatile ring resonator or these non-volatile non-reciprocal ring resonator memory cells. And because these have magneto-optic materials on them, if you encode a magnetic field radially outward versus radially inward, you get a phase shift that is dependent on whether or not it's the clockwise versus the counterclockwise mode in these devices. If you do a balanced photo detection at the very end and compare the clockwise versus the counterclockwise transmission, you can actually get both positive and negative numbers just by switching the direction of the magnetic state in your ring. And by applying an electrical current to these integrated electromagnets that are integrated on chip, you can switch the state of these materials and integrate both continuous tuning, and if you add this Kofi B magnets, you can actually hold that magnetic state without any sort of energy. So the way that you would actually do computation with this is you'd have an input that has different colors of light that are resonant with these different microring resonators, and you would put your probe as at one side of, for example, these purple versus these red resonators. But if you had a reciprocal device, you can only tune it in one direction. So you're comparing the through and the drop port, and by doing that, you can get both positive and negative numbers. This has been demonstrated in the past by Paul Purknell's group and Bob and Sastry's group. When you use non-reciprocal, now you're splitting the input and you have two through ports that are exciting both the clockwise and the counterclockwise modes, and therefore you have access to much higher extinction ratio because you're comparing the resonance dips to the transmission ports. An additional benefit is in comparison to reciprocal weight tuning, which doesn't have a symmetric function, we have access to an anti-symmetric function because we can cause a splitting of this resonance in either direction. And so we have access to both positive and negative numbers with a relatively small phase shift because we're comparing the resonance shift, the relative splitting. So this non-reciprocity leads to symmetric weight encoding of both positive and negative numbers, which is important for neural networks. So this was all, kind of overview simulation, but it works in theory as well, or in practice as well. So you can see from the experiment, we can tune, depending on where we place our probe, both positive and negative numbers between 0 or -1 and +1. But what we have in the DC state is when we are applying constant current, we're heating up the device. And so we see this quadratic shift depending on the current, which is due to Joule heating, which is a reciprocal effect, right? So the non-reciprocal splitting, you can see that the resonances are on two opposite sides in the experiment, but we have this overall Joule heating as well. So if you do this quickly, so if you send a pulse and you're fast enough, you don't actually heat up the material or the device. So in this case, we're sending high speed, so 2 nanosecond pulses, and showing that we can achieve, PAM4 weight setting. In this case, 2 bits of precision, which isn't much, but this is limited by the actual arbitrary function generator rather than the device itself. And again, we can demonstrate with another arbitrary function generator on-off keying. So we can set weight levels between -1 and +1. But the key thing here is that the minimum programming energy is in the hundreds of femtojoules per bit. The maximum programming speed, as you can see from this example, is 1 nanosecond. And key is the driving voltage is in the millivolts range, because this is a current-based approach, and therefore it's directly compatible with CMOS because we're talking about milliamps of current at, millivolts of voltage, which, if you chain enough MOSFETs together, you can drive that, yeah. So to enhance the energy efficiency, you can also demonstrate non-volatile weight encoding. So if we send programming current in one direction, turn it off, and then measure the resonance, we can see a characteristic hysteresis curve in this case, due to the fact that we have these Kofi B magnets on top. And so these measurements are after the current is turned off, and you can see a clear hysteresis shift both in the positive direction and the negative direction as we reverse the current. And really exciting about this platform is the fact that we have demonstrated billions of rewrite cycles. This is 10,000, I think, times better than any other non-volatile optical memory cell that has been demonstrated to date. The limit here is just the humans. Maybe in the age of AI, we can automate this measurement better. But after 3 days of measurements and having to realign the setup over the course of those measurements, they got tired and didn't measure more than 2.5 billion cycles. Okay, so that's weight stationary architecture. And in the last few minutes that I have, I wanted to talk about output stationary architectures as well. So instead of weight or fixed weight architectures where we are encoding the weight matrix A and sending through optical pulses in B, where we're limited by the physical hardware here, we can also do time multiplexed architectures where we're taking matrix A and matrix B and streaming them in time. So now we have access to a temporal dimension, which is no longer limited in terms of our hardware. We have one dimension that is limited in terms of our hardware, so how many times we have to, dice these matrices up. But the output matrix is, the final result. The sub matrix is the final result. We don't have to add up a bunch of different reconfigured matrices to do this. Additionally, if we multiplex in time, we have a much lower requirement on our ADCs, our analog to digital converters, which saves a ton in terms of energy. So in this case, if you send, optical information through at 10 gigahertz speeds, you have to measure it at 10 gigahertz speeds to capture that data. However, in this case, you can still send it at 10 gigahertz speeds and then sample after you've sent through your entire submatrices here. And this leads to, for problems that are much larger than the matrix, physical matrix that you can encode on photonic hardware, this leads to a significant improvement in terms of both energy efficiency and even latency if you take into account the time it takes to reprogram the array. So a way that we are looking to implement this is we are looking at our incoherent matrix vector multiplier and then just changing the inputs and outputs. So in this case, we're taking a matrix A, the rows of matrix A and the columns of matrix B, for example, and we are interfering them on this mesh network, this crossbar array network. And at each of these sections, we can do homodyne detection. And therefore, if we integrate over time and we take the difference between the input or the output intensities from these beam splitters, if we put a 50-50 beam splitter right here, we get twice the dot product of these two input vector electric fields. So we experimentally demonstrated that for a single unit cell. Here we have signal A and signal B, which we can control both the amplitude and phase with MZIs and phase shifters. And we compare the output of these two after this integrated beam splitter. And as we integrate over time, we do one sampling. Ideally, you store this up on a capacitor and you do one sampling on your ADC at the very end, and you get your final result within 3% of ideal in this case. And in this case, we were mostly limited by the extinction ratio of our modulators rather than anything else. Doing this coherently also gives you access to complex encoding of information, which is quite a benefit. Not only do we have access to both the imaginary or the negative side of the real number axis, but we have access to both the real and imaginary plane. And this allows us to encode for the same signal to noise ratio to the n more bits for the same signal noise ratio. And there's a nice work that's currently on arXiv called QuamNet, which was talking about the energy efficiency of using complex neural networks that leverage both the amplitude and the phase of optics at the same time. So we can demonstrate that with our system, that we can do multiplication with complex numbers as well as real numbers. So how do we scale this to 2 dimensions? Kind of the title of this talk was scaling, right? So scaling this to 2 dimensions, we can use our crossbar array and include a beam splitter, 3D beam splitter, and output to grading couplers. And if we image these grading couplers, everything out of the grading couplers, everything after this 3dB splitter is just intensity. It's just an intensity measurement. So that's we don't have to maintain any sort of phase coherence or mode coherence off chip, just on chip, and which is easy to do with single mode waveguides. So the system that we have is this. We've got our photonic circuit here. We image the output of these grading couplers on a near IR image sensor, which looks something like this. So in this case, this is a 4x4 matrix where we have to sample, essentially twice that in terms of, the number of grading couplers. So one for positive and one for negative. If we do a sweep of the phase of these input modulators, we can see that we get, this complementary interference pattern as we would expect. If we take the difference between these two, we can, encode both positive and negative numbers. And so once we, run our modulators very quickly and we do a single image detection, we can just compare the relative intensities of the accumulated photons that have been collected by our image sensor and get the resulting matrix at the output. So an example of, kind of what this looks like with higher laser power and illumination. So you can see the grading couplers versus lower illumination power or lower laser power without illumination is this. So we would, basically take snapshots, compare the relative pixels, and then that would be the output matrix. So we are currently looking at, seeing ways that this can scale up. There's a lot of claims out there that photonics can, achieve petawatt or petaops or exaops, compute. But if you have no way of actually inputting the data, that is, kind of a key limitation on the engineering and technical side. So we find that, if we take a 128 by 128 photonic crossbar, what we're really limited by is not the crossbar or the photonic components, it's the high bandwidth memory just to feed in that information. So in this case, we had to actually limit our precision to integer 15 or integer 5 just because you completely saturate the throughput of this high bandwidth memory to high bandwidth memory modules just by designing the architecture. So it's important to consider this from the architecture standpoint as well as the optics standpoint as well. So yeah, the core of this is a photonic crossbar array. And in this, we're assuming that we can integrate the photodetectors on chips, and we're not limited by 3D integration of a camera and such, which would not be particularly practical for scaling this out to data centers, for example. It's quite efficient. So the throughput from one of these crossbars is quite competitive with an A100. We're talking about an A100, which has, tens of thousands of 4x4 tensor cores versus, something that has just a single optical crossbar. It's always dangerous to compare with digital, but there we have it. Okay, so with that, I'd like to thank my lab, our collaborators on the magneto-optic work, and our collaborators on the reconfigurable multifunctional phase change memory work, and specifically Sadra, who's done a lot of has gotten a lot of the results that you see here. So yes, thanks.
Okay, beautiful talk, amazing development. So, any questions? Yes.
How do you program the individual magnets?
That's a good question. So you can program the magnets just by sending a current through the integrated electromagnet, and so the strength of that current will preferentially switch a certain number of those bar magnets. So a way to improve this would be we didn't try this in this first experiment, but if you wanted finer grain multi-bit configuration, you can change the shape anisotropy of those bar magnets, and so some of them will switch at a lower magnetic field than others.
Very versatile. Especially talking about in comparison to other exosomes, so about challenge resistance, scaling them, and in fact, in one of the things like continue to go the way for it to be scalable.
Yeah, that's a good question too. I open myself to those kind of questions when I say scaling. So one of the things that makes me encouraged about this approach is that there's a startup working on this for LiDAR. And what this is a 32 by 16 array where they have almost the exact same thing. They have a local oscillator. They're actually sending light out, collecting it back. They have an integrated balanced photodetector that runs at hundreds of megahertz speeds. So pretty much what we want. All we would need is a capacitor added onto that and, you know, sampling it. Yeah, but yeah.
If you compare it with other platforms, and Finland, for instance.
Yeah. This was inspired by a lot of his work. Yeah.
Better.
So they proposed a free space approach to this. I don't think that they've demonstrated an integrated photonic approach that was coherent anyway. So they have an integrated photonic approach that's distributed over fiber. I forget exactly what it's called, but it was between Lincoln Labs and MIT. So that's incoherent matrix vector multiplication. So you're limited by the positive real axis, right? This is coherent, so you can have access to the complex plane. It's integrated on a chip, and it's a way of scaling it up to 2 dimensions, where you are not limited by, you know, free space, mode matching, spatial mode matching, coherence lengths, and stuff like that.
How does it translate the size of the matrix that you can process? Of course, with your technique, you can break into the blocks.
Yes, yeah. You can break into blocks. It's really limited by fan out loss. But if you integrate over, one of the benefits of doing this is if you integrate over long enough time, you get square root of n decrease in your signal to noise ratio. So if you have a fixed amount of precision, you have a long enough vector that you're integrating over, you can handle very low amounts of optical power. Yep.
Beautiful.
Thanks.
Let's take speaker again.